In this video we're going to look at three more circle theorems, all to do with angles on the circumference. So let's start by drawing a circle, centre here. And we now need to draw a chord. So if I draw a chord going across the circle, so cutting the circle at 2 points. Now what I'm going to create now is a classic bow tie shape. So we can draw across to the other side here, and similarly like this, and then complete the bow tie shape, if you like, two similar triangles in fact. And that's the basis for the theorem. Now the theorem is that these two angles that are sharing the same chord at the bottom here, these two angles, or any two angles that share the same chord, two angles on the circumference must be congruent. They're going to be the same. Question is, how do we show that? So let's call this problem A. Problem A then is to show that angles on the same arc, subtended by the same arc onto the circumference, will be congruent or equal. So let's label up our triangle here, our two triangles. So we've got, let's say, A, B, C and D. And the centre, I'm going to avoid using O, I'm just going to call this E, because this isn't the centre of the circle, so I'm just going to call this E. So to show that CAD is equal to CBD, okay, these two angles here, that's what we want to try and prove. What I'm going to do is draw to the centre, because what I want to take advantage of is the idea that the angle at the centre is twice the angle at the circumference, which is something we proved previously. Okay, so let's draw up to the centre now. Draw from the centre down to here, and again we can label this O. Let's just make that a bit neater. Okay. So now, how do we prove that these two angles are the same, are congruent? Well, let's write down that, first of all, angle CAD then, CAD, must be, so CAD, half the angle at the centre. So what I'm going to do in fact is use a little bit of algebra here and just call this X, let's call this Y, and let's call this Z. So angle CAD is X, okay, and X has got to be equal to a half Y. And the reason, which we'd write up fully usually, but I haven't got room here, is because the angle at the centre, the theorem is, we've already proved, is that the angle at the centre is twice the angle at the circumference. So I'll just call that the Arrow Theorem and symbolise it with an arrow. So that's the reason. Okay, well if that's the case, then we've also got the same thing going on here. They're subtending the same arc. Let's just make it clear that we're talking about this arc here, this arc that goes from C to D. So if they're subtending the same arc, then angle CBD, which equals Z, well that's also got to be half Y, for the same reason. And so we conclude that X must equal Z, which was to be shown. So there you go. Now you could substitute values in here, so you might well get a problem that says X equals 50, Or you might get, or z equals 50, and you've got to find x. You might get this construction in the centre, you might not. The final thing, though, to point out before we move on to the next theorem is that there are two more congruent angles at the bottom here. So if we just remove this and instead look at the arc at the top here, if you turn your head to one side maybe, you can see that we've got, again, two angles subtended by that arc. So if we said this was angle A, all the way around here, and this was angle B, then similarly A must equal B by exactly the same reasoning, so we could prove that as well. So we've got x equals z and A equals B. Okay, let's move on to problem B. So with problem B, again, let's draw a circle. So center it here. And this time what I'm going to do is I'm going to draw a chord again, but I'm going to now draw two chords and then join those together to make what we call a cyclic quadrilateral. So this is called a cyclic quadrilateral. And again, the problem is to show that if I have, say, let's say that this was 100 degrees at this point here, then this would be, well, not actually congruent, not 100 degrees, but what we call supplementary. So this would be 180 minus 100, so this here would be 80. So the theorem is that opposite angles in a cyclic quadrilateral add or sum to 180. The cyclic quadrilateral theorem. So that's what we have to show. How do we go about doing it? Okay. Well, again, we'll use our very useful theorem, which is that the angle at the centre is twice the angle at the circumference. So if I draw to the centre here, then again I can use a little bit of algebra to prove the theorem. So I've got, let's say I've got to find x here, and I know that this is, well, let's call it 180 minus x. Okay, so that angle should be, according to the theorem, 180 minus x. So can I prove that? So first of all, let's label up our diagrams. So again, A, B, C, and D, and this time O for the centre. So O could be the centre here. Now, what is the angle AOC, the reflex angle AOC? Well, it's twice x, so it's twice the angle at the circumference. So let's write that down first of all. So angle AOC, the reflex angle, must equal 180 minus x. Sorry, not 180 minus x, must equal 2x. Okay? Must equal 2x. Okay. And again, it's by the Arrow Theorem, or the theorem that the angle at the centre is twice the angle on the circumference. So same reasoning. So now we've got, and I'll use a different kind of pen here so we can see it clearly. So I'm working out here, we've now got 2x as this reflex angle, the angle that's greater than 180 degrees, which is there. So what about AOC, not the reflex angle? Okay. Well, that must be, so angle AOC let's put, therefore, angle AOC equals, what is it? It's going to be, all the way around is 360, so it's 360 minus the 2x. Okay. So, how do we then go on to prove that ADC is 180 minus x? Well, if we rewrite this to factor out 2 times 180 equals 360, and 2 times x equals minus 2x. So factor out the 2 like that, then it's clear that therefore angle ADC must equal 180 minus x, which was to be shown. Now, lastly, let's draw another circle, just putting it a little bit higher. And what we're going to prove here is the alternate segment theorem. So let's make a chord going right across the circle. And from this point here, let's draw down to make another chord. So we've got one angle on the circumference. If we join it together, we've got a triangle in a circle then. So what the theorem says, the alternate segment theorem, is that if we draw a tangent, let's say from this point here to that triangle, so tangent to the circle but touching at this point here, you have to be a bit careful because it's not quite down here, so draw it at a slight angle, like that. Okay, if we have a tangent, then the alternate segment theorem says that the angle in between the chord, between this chord here, let's say, and this tangent, the angle between a chord and the tangent will be the same as the angle in the alternate segment. That's why it's called the alternate segment theorem. So what does it mean by the alternate segment? Well, this is the main segment that we're first focusing on. So it's this angle here between the chord and the tangent. And the alternate segment is what's left, the unshaded region, in other words, the unshaded part of the circle. And so we look opposite and we see that this angle here is apparently equal to this angle here. So that's what we've got to prove. In fact, there are two. So if we, let's just unshade that. If we look at this segment here, the angle between this chord and the tangent must have the same property. So the angle here will also be the same as the angle in the alternate segment, so the angle opposite, which is here. But how do we prove that? Okay, well, let's call this problem C. First of all, let's label it up. So we've got a triangle, so we'll call this A, B, C. Now, our tangent needs a couple of ends here, so we'll call this D and E. And guess what? We're going to prove this in the same way. We're going to draw a construction. We're going to add a couple of lines. We're going to draw up to the center. So if we do that, we can then make use of the theorem that says that the angle at the center is twice the angle on the circumference. So let's go ahead and do that. Okay. So what have we got? Let's start by showing very clearly what it is that we want to prove. So it's this angle here, which we can call x, that we want to prove that that is equal to this angle here, which we can call, let's call it z again. So this angle here. So x equals z is what we want to prove. And there's a few more steps here, but I'll spell them out, but notate them quite briefly. But of course, what we want to do is write out the reasons every time as fully as possible to get all the marks particularly if we're being examined in a test. So I suppose I should go back here and say, well, that was angles around a point are equal to 360, so just using a symbol, but if you write them out fully. And then here again we had the arrow theorem to prove this one. Okay, so in this case, so we've got x, so that's angle EAC, but we've also got this z here. What I'm going to do to start with then is use the arrow theorem, I think, to define this angle in the middle. So let's write that down as angle AOC, angle AOC, and that must be twice ABC. So 2 times ABC, I'm not going to write it out fully, so I'll just write 2Z. So angle AOC, the angle at the centre, is twice the angle at the circumference, which is ABC, or we're defining it as Z. And again, the reason is the arrow theorem, or the angle at the centre, is twice the angle at the circumference. So that's our starting point, and let's just draw that in. So a little bit of working helps to see very clearly what's going on. Now the next thing I want to do, because I'm trying to get at this angle here, is I want to use the isosceles triangle theorem. So this side here, OA, must equal OC. And that means that the base angles must be equal as well. So if the base angles are equal, well, each one has got to be 180 minus, so we've got 3 angles in a triangle, so it's going to be 180 minus this 2z, so each one of those must be half that, so in other words 90 minus z. And usually I would write that out more fully than I am here, but for the sake of brevity, let's just explain that, and then you can notate it yourself. Okay, so that's 90 minus z. Let's just check it. If we had 90 minus z here, then if we add them together, we'd have 180 minus 2z plus 2z is 180. So that's how we got this angle here. Now, let's notate it. Let's write it down in our proof then. So angle CAO equals 90 minus z. Why? Because of 2 reasons: angles in an isosceles triangle, and because of the angles, the sum of angles in any triangle. So sum of angles in a triangle add up to 180. So now that we've got 90 minus z, we need to do one further thing, which is remember that a radius and a tangent are always at 90 degrees. So OAE, angle OAE is a right angle. Just draw that on here, which in other words is 90 degrees. Let's put the degree symbol in. And those 3 things give us enough now to prove what we set out to prove, because x must be this 90 degrees, so the full 90 degrees. So x, let's just make that a bit clearer. Okay. So therefore x equals 90 degrees minus, let's put our degree symbol in here, 90 degrees minus z. Okay, 90 degrees minus 90 degrees minus z. And if you expand the brackets, you'll then get 90 minus 90 plus z, so x equals z, which was to be shown. So finally, just to note that we can use some of the theorems that we've just derived, not just rely on the theorem that says the arrow theorem, the theorem that says the angles in the centre of a circle must be twice the angle on the circumference. So we're going to use now some of the other theorems that we've just derived. So let's just summarise what we've got. We can use the arrow theorem and its variants, including the semicircle. We can use now the bow tie. So if you can spot the bow tie, that's a good one to use as well. We've also got now the cyclic quadrilateral. So I'll just write cyclic quad. So the cyclic quadrilateral. And we can use also things like the isosceles triangle theorem. Base angles of an isosceles triangle must be congruent. So the isosceles triangle, and other things like sum of angles in a triangle at 180 degrees. The angle all the way around sums to 360 degrees, angles on a straight line, and turn those basic axioms, and now these more advanced theorems that we use to prove. In this case, what we'll do is go back to the alternate segment theorem and use a combination now of these theorems to solve or to prove the alternate segment theorem in an alternative set of ways. So there isn't one way to prove a theorem like the alternate segment theorem, and let's now think of a slightly different way of doing it. So if I draw it slightly differently actually to start with, let's just do a very small chord now across here. We'll now subtend to the circumference, but underneath the centre, so to about here, here. There we go. So there's the angle subtended on the circumference. Now if we draw our tangent, then what we're doing is we're trying to prove that, so always check what it is you're trying to prove. We're trying to prove that this angle here must be the same as this angle here by the alternate segment theorem. So let's call it Z again, which seemed to work nicely before. Okay, now again we could use the arrow theorem or one of its variants. So in other words, we could draw to the centre and draw to this point here, and then the arrow theorem would work perfectly well, the angle at the centre being twice the angle of the circumference. But it's just as good an idea to produce this line, to extend it and create a diameter, and then draw to here. And then what we can do then is show that if I just label it up quickly, so A, B, C, D then is this extra point here. And we can show that we've got now a bow tie. Can you see the bow tie shape here? Okay, there it is. And we can work with that as well as other things, combining now these theorems. So we can say, let's say that this is, define this as y. Therefore, shared by the same arc, this angle on the circumference must also be y. Okay, so we can now say that angle DAC equals angle DBC, which we're defining as y. And we would need one other theorem really to get a grasp on this, and this can be the very simple semicircle theorem, which is a variant of the arrow. In other words, the angle at the centre is 180 degrees, so here we must have a right angle. So angle DAB, DAB must equal 90 degrees. The reason, angle in a semicircle, and again, reason here, the bow tie theorem. So usually we'd write out in words, so I'm just using symbols to save space. Now, One further thing we can do is identify another right angle here. So angle DBF is also 90 degrees. The reason it's the radiant tangent relationship. The radius tangent, the radius will always meet the tangent at 90 degrees. Now with these three ideas, we've got enough. You can see algebraically, we've got enough now to prove what we set out to prove, which is that x equals z. So we'll write, therefore x equals 90 degrees minus y, and z equals 90 degrees minus y, therefore x equals z, which was to be shown. Okay, so lastly, I'm going to try one more alternative proof. Probably be a little bit more elaborate. I think the more you go into these, the slightly more sophisticated you have to get. Instead of the bow tie, I'm going to use the cyclic quadrilateral. So let's just redraw this triangle, in fact, over to the right of the diameter now. And what we'll find is that we can then join this point to this point to create a quadrilateral instead of a bow tie shape. So I'm going to use the idea of the quadrilateral to again try to prove the alternate segment theorem. Okay, so let's just work out what we're trying to prove. We're trying to prove x. To save time, I'll remind us of this idea. We've got 90 degrees here because of the radius tangent theorem. I won't write it out because we did that before. And also we've got one up here, a new one, but again a right angle here because of the angles in a semicircle, the variant on the Arrow Theorem. So that starts us off. Let's label up as well our diagram. So A, B, C, D, and EF for the tangent. Okay, so how are we going to proceed with this? Well, it's going to be a little bit more complicated because we've got 1, 2, 3 angles here surrounding 2 angles and x to give us our 90 degrees. So that is what's going to create a little bit more complication. We're going to use this angle here as well. So let's label up first of all this triangle here. So we got x, we'll have y here, and we're trying to prove that the angle x, the angle between the chord and the tangent, the angle between the chord and the tangent is corresponding to and equal to, congruent with the angle subtended by the chord in the alternate segment. So in other words, this one here. Okay, so this is, we'll call it z. Okay, so we want to prove that x equals z, and we're going to go about it by saying first of all that the cyclic quadrilateral theorem tells us that angle CDA, so angle CDA, is what? Well, it's 180 minus y. It's supplementary to y. So we can write that in. 180 degrees minus y is this angle here. Okay, so 180 degrees minus y. And that's by the cyclic quadrilateral theorem. Right. Now, we've got 90 degrees here. We've got 180 minus y here. What do we have here? What's the angle here? Well, we're going to use the third angle is going to be 180 minus these two angles. So sum of angles in a triangle add up to sum of angles are 180. So we've got 180 degrees. So we'll say angle CAD then must be 180 degrees minus all of this. So minus 180 degrees minus y. We've got to be careful of our negatives here, and minus the 90. So minus the 90 degrees there. And if we expand the brackets, we've got 180 minus 180, so that 180 is going to cancel, and the minus times the minus Well, that's going to give us a plus. So we've got y minus 90. Reason? Sum of angles in a triangle. Okay, so I'm going to try and squash that in here. So y minus 90 is this angle here. Okay, so what have we got in here, the final one that we need to fill in here? Well, this must be 180 minus z minus y, because again, sum of angles in a triangle. So angle CAB is 180 minus y, minus z minus y, sorry, minus z minus y. And we've now got enough, if I just squash that in here, 180 minus z minus y, that's that angle there. We've now got enough to form our expression, so we've got x must equal then this angle 90, which encompasses all of these three angles, so we've got 90 degrees, minus, well, y minus 90, so in brackets y minus 90, like that, and then we've got to subtract this angle here as well, so that's going to be 180 minus z minus y. Okay, so what have we got? If we expand the brackets now, we've got x equals 90 minus y, and minus times a minus, so plus 90. And then here we've got minus 180 plus z plus y. And hopefully you can see that the 90 at the 90 is 180, minus 180 is going to cancel very nicely, and minus y plus y also cancel, leaving us just with exactly what we want set out to prove, the alternate segment theorem, in other words that x equals z, which is the only value we've got left here, so x must equal z, which was to be shown.